Here's a big deal, folks. The conservation of mechanical energy. I told you last week that the work energy theorem was a really big deal, like Newton's laws. Well, it is. It is. The conservation of mechanical energy, as we'll see in about a week or so, is just another way of repackaging the work energy theorem. So they're kind of, in my mind, they're similar. They're kind of the same. They're really the same thing. But conservation of mechanical energy is basically a statement about energy, which is hugely, hugely important. And although it carries the same sort of essence as the work energy theorem, it is presented in such a way that it is very user-friendly and over time becomes very, very intuitive. And energy is such a big deal in the universe, it can't be it's more fundamental than forces. First of all, what I want to do is define for you this thing called mechanical energy. Okay? Mechanical energy is given the symbol capital E. Okay? And it is defined as the mechanical energy of a system is the system's kinetic energy plus its potential energy. And there you go. It's simply the sum of the two kinds of energies that we have talked about. Kinetic and potential. You add them up and you get what's called the mechanical energy E of a system. That's it. This quantity, this sum, is hugely important because in many circumstances, it is conserved. And conserved in physics means it does not change over time. K can change over time, like when this bowling ball falls. Its kinetic energy changes as it speeds up. Its potential energy changes as its height as y changes, right? Its potential energy changes, its gravitational potential energy changes. So K and U individually change, but the sum of them does not. Let me be careful about the way I write this. E is conserved. Again, I'm not going to write it on the board, but that means it does not change when only conservative forces, the C stands for conservative forces, do work. E is conserved. That is, the sum of the kinetic and potential energies is conserved, does not change in time when only conservative forces do work. Okay? So, another way of writing this is that EF equals EI for any initial point and any final point. Again, we're assuming, for the sake of this video and for the next couple videos, that only conservative forces do work. Okay? When only conservative forces do work, this quantity, K plus U, does not change in time, and that makes mechanical energy a real fixed point, a real sort of guide star as we wander the thickets of physics here. Final energy for any given final point is equal to the initial energy for any initial final point. Another way of writing this is because, delta E is EF minus EI, right? That's the definition of delta. Final value minus initial value. Delta, that means that the change in mechanical energy is zero. That's sort of how you write this. Delta E is zero if only conservative forces are doing work. That's why we call them conservative forces. Because when they act, energy is conserved. When only gravity acts, that's one of our conservative forces, when only gravity is doing work, rather not just acting, but doing, has to be specifically doing work. When only gravity, say, does work in a particular problem or particular situation, then energy is conserved. Therefore, we say that gravity is a conservative force. That's where the term conservative comes from. Now, to show you how this principle works, and this principle is golden, I'm going to look at the bowling ball. The bowling ball that we set up on our 2-meter shelf, say a couple years ago, we walk around the house to shake the walls a little bit. It's going to roll off. Eventually, it's going to creep super slow, and then fall to the ground. And we're going to say that its initial velocity is 0 because it's moving so slowly before it tips over the, sort of falls over the cliff there, that its initial velocity is going to be 0. This will be its initial position. This will be its final position. We want to know what V sub f is equal to. And I want to show you how to use this principle of the conservation of energy, rather this principle. This is the definition of mechanical energy. This is the principle. This is the conservation law right here. Delta E is equal to 0. Okay. And again, EF equals the I is just another way of writing delta E is 0. Right? It's the same thing. We want to use this principle to determine the speed of that ball. We don't want to use Newton's laws. We don't want to use kinematics. We're going to use energy. Okay? So, how are we going to do this? How are we going to figure out what V sub f is equal to? I'm going to do it right here. Well, we're going to figure out what E sub I is equal to. And then we're going to figure out what E sub f is equal to. Then we're going to set them equal to each other. That's the idea. Let's see what EI is equal to. Well, you know, the EI is going to be KI plus UI, right? If E is equal to K plus U, then initial energy is just initial kinetic energy plus initial potential energy. So that's going to be 1/2 MVI squared plus MGYI. Because this 1/2 MVI squared, that's just the initial kinetic energy. MGYI is the initial gravitational potential energy up at the top. Similarly, EF is going to be final kinetic energy plus, final potential energy, which is 1/2 MVF squared plus MGYF. Right? I'm just unpacking the energy here. I'm unpacking the initial energy. It's this thing here, 1/2 MVI squared plus MGYI. That's the initial mechanical energy of the bowling ball. The final mechanical energy of the bowling ball is its final kinetic energy plus its final potential energy. Now let's look at our picture here and figure this out. What we're going to do in the end, of course, right, is we're going to, I'm not going to do it yet. Let me just ask this question. The next step in the procedure, once we have this written down, is to figure out which of the, well, we have 4 terms. We have 2 for initial energy and 2 for the final energy. And when I say energy, I don't always put the word mechanical in front of it. If I say the word energy without referring to kinetic or potential, I mean the mechanical energy. Okay, sometimes called total mechanical energy. So what is the initial speed of the bowling ball? It is 0. Remember I said it was just dropping off the shelf very slowly. So it was essentially at rest. Right? It took a couple years for it to crawl a couple inches as we bang around the house. Okay. Y sub I is not 0. It's 2 meters. Right? In fact, we can put subscripts on these. Right? Y sub I is 2 meters. Y sub f is 0 meters. Okay. So, initial energy is all potential energy. Right? It's all potential. There is no kinetic energy initially. Now let's look at the final situation. The ball It hasn't hit the ground yet, right? This is the instant that it hits the ground. We want to know at what speed it strikes the ground. Okay, and when it has that maximum speed up before it hits the ground, it hasn't yet hit the ground yet. So its speed is not 0, it's going to be v sub f. So v sub f is not 0. That's the thing we're trying to find. But y sub f is 0. Because it ends up on the ground, which we have defined to be y equals 0. Arbitrarily, we could have picked any value, any point of y and called it 0, but we picked the floor. It makes the most intuitive sense. So the final mechanical energy is 1/2 mvf squared. Now the conservation principle tells us that these two are equal because only gravity is doing work here. Only a conservative force is doing work. So those two are equal. So we can write 1/2 mvf squared equals mgyi. This is EF. This is EI. You see that? And we want to solve this for v sub f. First thing I want you to notice is that we can divide both sides by m and get rid of the m. It doesn't matter what the mass of the bowling ball is. Now in the previous video I actually gave you a value for m, but it doesn't matter what it is. Those cancel out. So what we're left with is, turned to a little of a mess here, is 1/2 vf squared equals gyi. Okay. So we can solve this for v sub f. V sub f, multiply both sides by 2 and take the square root. Okay. This is equal to square root of 2, 9.81 meters per second squared times 2.0 meters. And you get, I believe if you do your math correctly, you'll get 6.3 meters per second. And there's your final answer. That is the speed. And if you want the velocity, of course, it'd be down, it'd be negative. I just asked for the speed though, so the speed is 6.3. If we wanted to ask for the velocity, you take the negative root of this and put a negative sign on front of it. But I just asked for the speed, so there it is. That's how fast the ball is going when it hits the floor. Okay? All right, now, one last little picture I want to give you. What has kind of happened here is, imagine we've got two buckets. So we've got the kinetic energy bucket and we've got a potential energy bucket. Okay? Actually, let's turn that around. Let's say we have a potential energy bucket. We have two buckets. Okay, we've got a potential energy bucket and a kinetic energy bucket. This is just a way of thinking about energy and thinking about conservation of energy. And this example provides a nice case. At the beginning, all of our energy is potential. So this one is just totally filled up with our water, our energy, right? In the same way that a bucket is full of water, we can think that we have all of our energy in a single bucket. The water represents the total energy of the system, the total mechanical energy of the system. So this is initially. Finally, what we have are the same two buckets. But all the water has been poured out of the potential energy bucket into the kinetic energy bucket. Finally, all of our energy has been transferred from potential energy to kinetic energy. We have lost none of it. That's what conservation of energy means. Conservation of energy means that throughout this whole process, as we're pouring the water out of the U bucket into the K bucket, we're not spilling anything. Okay? We're not spilling anything. If only conservative forces are doing work, we're not spilling any water. We have gotten every last drop out of the potential energy bucket initially into the kinetic energy bucket finally. The amount of energy in this bucket is equal to the amount of energy in that bucket. Started off in U, ended up in K. Lost not a drop. Initially we had none in K, finally we had none in U. Okay? When conservative forces are acting, doing all the work, that means we don't spill a drop. All the energy gets transferred from one form into the other without any losses whatsoever. So the potential energy here is equal to the kinetic energy there. That's conservation of energy.